Good morning, students. This will be a lecture on how to find the steady state error for a non-unity feedback system, and also some of the pulse transfer function examples. So, as you know, as we have already seen the last class, the steady state error for unity feedback system, because the steady state error is defined for unity feedback system. What you have to do when a non-unity feedback system, that is h of z, is not equal to 1, in that case it is not unity. Okay, so when h of z is unity, it means this block will not be there, and you will have directly the actual output, or cz is directly fed to the input. That is what we have seen. So now if h of z is not equal to 1, that means non-unity, how will you design, or how will you find the steady state error and also the static error constants Kp, Kv and K? So that is the objective of this lecture. So here if you have h of this is the example that is given to you, where you have a feedback h of z which is not unity. Okay, so I can write this or I can redraw this block diagram as like this, because here this is h of z is already there, and if I add -1 in the feedback path, I have to add a +1 also, so that these two get cancelled, and finally you will get this one itself. But our aim is not to cancel out after drawing this. So we need, now you can see that I have added the actual output is fed back with a -1 gain. Okay, so I must feed back another with a +1. +1 is as if it is a like this unity feedback. Okay, so what will be the result of these two? So that is here like this. Okay, it is hz -1. Sorry, so hz is coming over here, and -1 is also coming. So hz -1 in the feedback path. That feedback pass can be added. Okay, so only the feedback pass alone, it is not added with the feed forward path. So now you have a loop, okay, where this is the inner loop. There are two loops here. This is the outer loop and this is the inner loop. So always inner loop can be simplified, as you know. It is gz by 1 plus gz hz, if hz is the feedback path, feedback transfer function. But here the feedback transfer function is now hz -1. So it will be gz divided by 1 plus gz into gz inside the bracket hz -1. So what is that? It is gz over 1 plus gz, if I take the bracket out, gz into hz minus gz, isn't it? So 1 plus gz hz minus gz will be this inner loop. So that will be now the feed forward path in this. So that means whenever you have a unity feedback system, here that can be replaced with a non-unity feedback system with its gz, as say for example, if g dash z is the non-unity feedback cascader or feed forward transfer function, then g dash z will be equal to gz by 1 plus gz hz minus gz. So that is the essence. Now you can see that this is actually the same as that we have done in the previous classes. Like it is a unity feedback now, but it was having a feedback with h of z which is not equal to 1, that is counted over here. You see in this block, or in this feed forward transfer function, this is the feed forward transfer. So here if h of z is equal to 1, so that is the first case. So the previous examples were that we have done. So where h of z is equal to 1 means what happens here for this transfer function? It will be gz over 1 plus gz into hz. Hz is 1 means into 1 minus gz. So it will be gz minus gz, and you will end up with gz by 1, or it is as if it is at gz itself, where it is having h of z as. So if you start with a non-unity feedback system, and if you have h of z as unity, you can directly put that value, thereby you are getting the gz itself. So this is the outcome. So how will you solve, or how will you find the steady state error and the static error constants like Kp, Kv and K as we have seen for unity feedback, because it is the steady state error is defined for unity feedback. So only thing is, if it is you are given a non-unity feedback system, then you must convert it into a unity feedback system. So that is here. Now it is converted to a unity feedback with this as the GZ. So we will see how they can be derived, like the non-unity feedback steady state error ESS is nothing but E of infinity. Also I have written here also, it is E of infinity is ESS. Okay, so for sampled step input, so when the input is a step, you know that you are going to find the, in terms of Kp, the position error, static position error constant. So for non-unity feedback system, this is the thing that we have already obtained from here, that is Gz over 1 plus Gz Hz minus Gz. So that is a non-unity feedback system, means Hz is not unity. So, and this is the block diagram, okay, that is obtained from the previous calculation. So that is, let G dash Z is equal to Gz by 1 plus Gz Hz minus Gz. So that this is replaced with G dash Z. And then we know that E of Z, that we have already found in the last previous sections, that is E of Z is equal to Rz by 1 plus G dash Z. Okay, so here you know, if you write here also this as G dash Z, then you will end up with this answer, that is R of Ez is equal to R of Z minus Cz, and Cz is nothing but, if this is G dash Z, then G dash Z into Ez. Okay, so Ez will be equal to Rz, okay, minus replacing Ez in terms of this G dash Z and Cz. Okay, so you will get it as what? You will get it as E of Z is equal to Rz by 1 plus G dash Z. So the steady state error ESS is equal to limit k tends to infinity E of k. Okay, that is equal to limit z tends to 1 z minus 1 by z into E of Z. That is by the definition, or by the you know that it is by the final value theorem, that is that we have already proved. Limit k tends to infinity E k, which is nothing the final value of E of k, that is your steady state error, and that's equal to limit z tends to 1, that is derived already z in the last module. So z minus 1 by z into E of Z. So to find ESS for a unit step input, what you will do, the R of k is equal to 1. So this Rz is nothing but the Z transform of R of k, which is Z by Z minus 1. So Ez is can be written as 1 over 1 plus G dash Z into Z by Z minus 1. And what is E of k when k tends to infinity, which is something but the steady state error, is equal to limit Z tends to 1, Z minus 1 by Z into Ez. Ez is nothing but this one, and we are replacing Rz by Z by Z minus 1. So 1 over 1 plus G dash Z into Z by Z minus 1. So what happens here? Z get cancelled, Z minus 1 get cancelled, as in the previous only example, also previous calculation with the unity feedback also we got this cancellation as same. But only thing is here the E infinity is going to be equal to 1 over 1 plus, as I already told you, the limit can be applied inside, because 1 is independent of Z. So whatever may be Z, it is not depending on this constant 1. So 1 over 1 plus limit Z tends to 1 G dash Z. In the previous unity feedback you got it as GZ, but G dash Z now you know it is G dash Z is GZ by 1 plus GZ HZ minus GZ. So that is, this one is replacing with the position error constant, the static position error constant for a non-unity feedback system. Okay, so that is Kp dash I have put, just to note the difference between Kp and Kp dash, because Kp dash you know that this it is limit Z tends to 1 G dash Z. What is G dash Z? That is this one, that is limit Z tends to 1 Gz over 1 plus Gz Hz minus Gz. So this is the final value, or the value Kp, the steady state static position error constant you can calculate, and from the static position error constant you can find the ESS, the steady state error, or E of infinity, that is equal to 1 over 1 plus Kp dash. And non-unity feedback ESS for sampled. Now we have already found for sampled step input. Now we will go on finding the sampled ramp input. You know that for ramp input R of k is k and R of z is equal to Tz by z minus 1 the whole square. This is already done. Okay. So then E of infinity, that is nothing but the steady state error, is equal to limit z tends to 1 z minus 1 by z into what? Into this Rz by 1 plus g dash z, where only thing is Rz is changing to there is a unit ramp function. So ramp as it is sampled ramp Tz by z minus 1 the whole square. So 1 over it is, you can take, you can see here also z and z get cancelled, and z minus 1 and z minus 1 the whole square is cancelling out, and it is ending up with a denominator term as z minus 1. So 1 over, okay, and I am dividing by t, the t is nothing but, you know, this is sampling period. Dividing by t in the numerator and denominator, you will have limit z tends to 1, z minus 1, it is in the denominator, into 1 plus g dash z divided by t. So that is equal to 1 over, this again 1 over t can be taken out of the limit, because limit it is a constant value, sampling period. It doesn't depend on the limit z tends to 1. It is not a function of z, that's why. So 1 over 1 by t limit z tends to 1, z minus 1, I am taking out the bracket, z minus 1 into 1, that is z minus 1 plus z minus 1 into g dash z. Okay. So that is equal to 1 over 1 by t limit z tends to 1, z minus 1, because here this will go when z tends to 1, 1 minus 1 0, but here we cannot just like that negate that. Why? Because we have seen already for the other examples, if g dash z is having a pole or having a, in the denominator discrete time pole at z is equal to 1, that means z minus 1 is there in the denominator, that will get cancels, so that we will say usually as a type 1 system and so on. So here E infinity, that is the steady state error or the value of error or the at this steady state. So that is equal to 1 over 1 by t limit z tends to 1, z minus 1, this has gone because it is nothing to do with, it has no multiplication factor, but here it is multiplied with g dash z, which is according to the system or according to the g dash z value, and that g dash z you are finding as gz by 1 plus gz hz minus gz, depending on that value or that transfer function nature, this will have a value, a constant value or a non-zero value depending on this. Okay, so that is why E of infinity is equal to, we are giving it as 1 over kv dash, where kv dash is nothing but 1 over t limit z tends to 1, z minus 1 g dash z. So we will say that the kv dash is the static velocity error constant for non-unity feedback, because we have already given kv as the static velocity error constant for unity feedback. So this is kv dash, where kv dash is equal to 1 by t limit z tends to 1, z minus 1 into gz by 1 plus gz hz minus gz. This is coming over from the previous, that is we have already shown you what is g dash z. Okay, so this is g dash z. This is coming over from the result that we have analyzed for finding h of z is not equal to 1. So that is gz by 1 plus gz hz minus gz. That's what g dash z. Here you can see that for the same. Okay. So that is for the steady state error, finding the steady state error for a sampled ramp input. So whenever it is a ramp input, you know that is d by dt is coming. That is why we are saying the static error constant as kv, the velocity error constant. And what will be the steady state error for a non-unity feedback system for a sampled parabolic input? So for the parabolic input, so we can find the steady state error. The parabola input, you know that usually it will be taken as r of k is equal to k square by 2. The similar thing we have done for the unity feedback for finding the value of k. So here Rz will be equal to what? It is t square z into z plus 1 by 2 into z minus 1 the whole cube. This we have already proved, or also it is there in the Z transform pairs table that is already given to you in the last module, that is already we have done the series also in that. So E infinity, that is the steady state error or E of k, E infinity is nothing but limit k tends to infinity, E of k, it is a finite value. of the error, that is the steady state error. That's equal to limit z tends to 1, okay, by final value theorem. It is z minus 1 by z into capital E of z. That capital E of z is nothing but that we have already done here. That's why it is not written again. Okay, here already it is written E of z. Okay, so rz by 1 plus g dash z, where only rz is changing here. So here you can see that limit z tends to 1, z minus 1 by z into 1 over 1 plus g dash z into rz. Rz for the unit or the sample parabolic input is t square z into z plus 1 by z into z minus 1 the whole cube. So here you can see that some of the things will get cancelled. Here also z and z will get cancelled, and z minus 1 and 1 of the z minus 1, or out of the z minus 1 the whole cube get cancelled, resulting in z minus 1 the whole square. And what about the numerator? It is having only z plus 1. So of course you can apply the limit there as z is equal to 1. So it is 1 plus 1, 2 here, and the denominator also you have in this sampled parabolic input 2. These two get z plus 1 as z tends to 1, it is 1 plus 1, 2 in the numerator, and 2 in the denominator will get cancelled, resulting in, again I am dividing the numerator denominator by t square. It will end up as 1 over, and also you know that 1 is not needed to apply the limits. So 1 over, it is the limit is going to the denominator. So limit z tends to 1, z minus 1 the whole square into 1 plus g dash z. That is this one. Okay, these two get cancelled, and z minus 1 cube, out of that 1 is z minus 1 factor is cancelled with this one. Okay, so that is why it is having z minus 1 the whole square into 1 plus g dash z. And as we are dividing the numerator by t square, we are dividing the denominator by t square. That is why it is the full divide by t square. Again, t is a constant value. It is a sampling period, so it can be taken out. So it is in the denominator itself, 1 over 1 by t square into limit z tends to 1, z minus 1 the whole square. I am taking out the bracket, that's what, plus z minus 1 the whole square into g dash z. Okay. So again, as we have done in the ramp input, the same. Here you can apply the limit as z is equal to 1. So 1 minus 1 0 square, that will be 0. But here you cannot just like that apply and put it as 0. Why? Because it depends on g dash z factors or g dash z poles. Okay. So if there are multiple poles at z is equal to 1 for g dash z, so it will have a denominator term as z minus 1 the whole square. We will say it as type 2 systems. So z minus 1 the whole square in the denominator, that means it will get cancelled, and you will have a non-zero finite value for this when you apply limit z tends to 1 for this denominator value. So that is, the denominator is taken as Ka here. So here you can see that this is like this, that is this already explained. So the steady state error due to the parabolic input, that is E infinity or SS, that is equal to 1 over 1 by t square into limit z tends to 1, z minus 1 the whole square, this one alone, this is gone already. So z minus 1 the whole square into g dash z. So that is nothing but we are taking it as 1 over Ka dash. That means Ka dash is equal to 1 over t square limit z tends to 1, z minus 1 the whole square into g dash z. So here Ka dash is this one. So Ka dash is the static acceleration or a constant for non-unity feedback, because that is why it is coming as g dash z. Instead, in the previous previous example or previous theory where we have a unity feedback, then we have given it as the same thing with a Ka is 1 over t square limit z tends to 1, z minus 1 the whole square g z. Okay, so here as there is a non-unity feedback, that's why we are finding g dash z in terms of g z. So what is Ka dash then? When you apply the g dash z value, that is Ka dash will be equal to 1 over t square into limit z tends to 1 into z minus 1 the whole square into g z by 1 plus g z h z minus g z. So this is from the first theory of non-unity feedback. Okay, so we have already found the Kp, Kv and Ka values for the different inputs, like sampled step input, sampled ramp input and sampled parabolic input. So we will move on to do an example on non-unity feedback. Yes, non-unity feedback steady state error. So this is ESS. So for the system given below, if t is equal to 1 second, the question is t is already given. There is a sampling period is given to you. So you can directly put that value of t as 1 second. Determine the steady state error due to a sampled step input, steady state error due to a sampled ramp input, also the static acceleration error constant, and steady state error due to a parabolic input. So of course for you to find the steady state error due to the sample step input, you need to calculate Kp, or that is a static position error constant for this non-unity feedback system. And also for finding the steady state error due to sampled ramp input, you need to find the Kv, that is the static velocity error constant for non-unity feedback system, because the system given to you is a non-unity feedback. This is H of Z. So the system is given to you like this, where H of Z is 1 over Z plus 0.4 and G of Z is 0.8 into Z plus 0.4 by Z minus 0.4. So the first thing is you have to find, or you have to make this block diagram unity feedback as we have done in the first case. That is, for that you have to find G dash Z. Okay, that's the first step for finding the steady state error and the static error constants. So here GZ is from here, from the example or from the problem given to you, GZ, this is GZ and this is HZ. Okay, this is the open loop or the transfer function, and this is the feedback transfer function. So GZ is equal to 0.8 into Z plus 0.4 by Z minus 0.5. So that's what it is written, 0.8 into Z plus 0.4 by Z minus 0.5, and HZ is given as 1 over Z plus 0.4. So HZ and GZ are there. As HZ is non-unity, that is, it is not unity, because you know HZ is equal to 1 over Z plus 0.4, it is not going to be one value, unity value. So first find out G dash of Z. So G dash of Z is equal to GZ over 1 plus GZ HZ minus GZ. So that is you have already proved it. Okay, so that is equal to 0.8 into Z plus 0.4 by Z minus 0.5. So here, that is here this is GZ divided by 1 plus GZ HZ minus GZ. So GZ is 0.8 into Z plus 0.4 by Z minus 0.5 and 1 plus GZ HZ. Okay, GZ is 0.8 into Z plus 0.4 by Z minus 0.5 into HZ is 1 by Z plus 0.4 minus 0.8 into Z plus 0.4 by Z minus 0.5. So here you can see that if I multiply the numerator and denominator by Z minus 0.5, this is 0.8 into Z plus 0.4 into Z minus 0.5, I am doing that to get cancelled, and then in the denominator it will be Z minus 0.5 plus 0.8 into that Z plus 0.4 and Z plus 0.4 get cancelled, and into Z minus 0.5 we are doing, that is also get cancelled, so that it will be only 0.8 minus 0.8 into Z plus 0.4 only, because we are multiplying with Z minus 0.5. Okay, so the result will be 0.8 into Z plus 0.4 by 1 Z. So this is taking out the bracket, that is 1 Z minus 0.5 plus 0.8 minus 0.8 Z minus that is here plus into minus 0.8 into 0.4 is 0.32. So this just like that you can add. Okay, that is 0.8 into Z plus 0.4 divided by 1 Z minus 0.8 Z, that is 0.2 Z minus this is what it is, these two are minus, so that is minus 0.5 minus 0.32, that is minus 0.82 plus 0.8, that is 0.02. So Kp is equal to limit Z tends to 1 G dash Z, that's equal to limit Z tends to 1, this is your G dash Z. Okay, so 0.8 into Z plus 0.4 by 0.2 Z minus 0.02. So you can see that you are getting a finite value and a non-zero value. So when you apply Z is equal to 1, it will be 1.4 here in the numerator, 1.4 into 0.8 divided by in the denominator 0.2 into 1, that is 0.2 minus 0.02, that is 0.18, and the numerator is 1.12. When you do this, you will get Kp is equal to 6.22. So if you get Kp, the question is you need to find the steady state error for a sample step input. So sample step input, the steady state error is defined by the definition, it is 1 over 1 plus Kp. So that is equal to 1 over, if you want you can put here Kp dash also, but for the time being I have put kp is okay. Only thing is you need that numerical value. So 1 over 1 plus kp dash or kp, here also kp dash, it will become the same. So it is 6.22, whatever it is, kp or kp dash. So 1 over 1 plus 6.22, that is equal to 0.138. For the given system, kp is, for the given system is a non-unity feedback. So the static velocity error constant is 6.22, and thereby the steady state error for the non-unity feedback system for a unit step input, or for a sample step input, you are getting it as 0.138. And the steady state error ESS for a sampled ramp input. That's the next question in the same problem. So here you are just calculating, that is kV is equal to 1 by t, limit z tends to 1, z minus 1 into g dash z. Again t you can put it as 1 second, it is given in the question. So the static velocity error constant for this non-unity feedback system will be equal to limit z tends to 1, z minus 1 into g dash z. So for this given example, you have already found g dash z. Here it is already found g dash z, that is 0.8 into z plus 0.4 by 0.2 z minus 0.02. So in that you can apply the limit, so that you will end up with a kV. So that is kV is equal to limit z tends to 1, z minus 1 into g dash z is replaced with this one. But as here you can see that g dash z is not a function of this. In the denominator you don't have z minus 1, it will not get cancelled. It is a type 0 system. We can say that g dash z is a type 0 system. So 1 minus 1 would be 0. So limit z tends to 1, kV will be 0. So the steady state error for the ramp input will be equal to 1 over kV, which is equal to 1 over 0 is equal to infinity. So for a sampled ramp input, the steady state error is going to be infinity. That means the given non-unity feedback system cannot be used for giving an input of sampled ramp, because it is going to give an infinite error where the system becomes cumulative error will make the system damage. So that's the inference. And again for the same example, you need to find the steady state error for the system for a sampled parabolic input, that is ESS is equal to infinity, is equal to 1 over k, where k is the static acceleration error constant. So k we have already defined as 1 over t square into limit z tends to 1, z minus 1 the whole square into g dash z. So g dash z already we have found as 0.8 into z plus 0.4 by 0.2 z minus 0.02. And ka is equal to 1 over t square. So t is in the question, it is given as 1 second. So t square will be 1, and limit z tends to 1, z minus 1 the whole square into g dash z. Replace g dash z by the value that we have already obtained for the example given. That is limit z tends to 1, z minus 1 the whole square into 0.8 into z plus 0.4 by 0.2 z minus 0.02. That is, here this is equal to, z is equal to 1 means 1 minus 1, 0 square. So it is again ka is going to be equal to 0. So steady state error for sampled parabolic input ESS, or you know that it is limit k tends to infinity, k or e of infinity will be equal to 1 over k or 1 over 0 here. So it is going to be infinity. Again, so it is proving that for the given non-unity feedback example given to you, it is not applicable to give an input of parabola, because if you give a sample to parabolic input, the steady state error or the error at the final value or the error at the steady state is going to be infinity, which is not at all advisable. Okay. So 5 typical configurations for closed loop discrete time control system. Here we have the 5 typical configurations for closed loop discrete time control systems. We can see that first one is again G of S. So here this G of S is where it's actually after the sampler. Okay, just after the sampler. So R of S here, R of S is actually coming first. Okay, and after that there is a sampler, and the output of that C of S is the output of C of Z. Okay, so C of Z will be equal to what? You will have, like I told you, C of Z will be having C star of S, then R star of S and S star of S. So C of Z will be G of Z into R of Z by 1 plus GHZ. And also you will have G1, this is the second combination where you have the sampler is connected after G1. So you can see here in the denominator, this is G1, G2, H of Z, because G1 and G2 are not going towards the, it is not passing through. If you are taking the C of Z from here, it is not passed through the. So please go through all these peculiar examples. So, and you can, these are some of the university questions that is asked. So how will you find the pulse transfer function? So same thing I have given here already. So just do it by your own. You need to do by step by step, writing C star S, writing E star S, and so on, that we have done in the first class of this module. And this also you can do this in the same way. Derive the expression. So obtain the pulse transfer function for the closed loop system. Also it is derive the expression for the pulse transfer function of an LTI system with a sampled data input. So this is a general question. So please work it on that. Okay. And this is another university exam question where it is 15 marks is given. Determine the pulse transfer function of the closed loop system given below for a sampling period of 1 second and open loop gain k is equal to 1. So here what you can do is you have to initially find this cascaded combination. The same thing for a zero order Horde we have done in the previous class. So what you have to do is you have to replace this first order Horde by its transfer function that is already derived in the Z transform module, that is module 2. So, and your G of S is here 1 over S into S plus 1, and also the question says you the T as 1 second sampling period, and K is also this gain. K is actually, it is a digital controller, that is proportional controller. K is equal to 1. Okay. So here for this example, for this university question solution I have shown here, that is the pulse transfer function by definition. Or what is pulse transfer function? It is C of Z by R of Z, that is equal to G of Z by 1 plus GZ. So how will you obtain G of Z if you are given here in terms of GS only? So G of Z is equal to Z transform of G of S, and G of S is nothing but it is a cascaded combination of these three, that is K into the Z transform of first order Horde, that is FOH is first order Horde, and 1 over S into S plus 1, and K is given as 1 here. So here G of S I am writing as K into 1 plus TS by T. K is actually given, and the transfer function of first order Horde is 1 plus Ts by T into 1 minus e to the power minus Ts by S into 1 over S into S plus 1, where 1 over S into S plus 1 is the your G of S in this question. Here you can see this is 1 over S into S plus 1. Okay, so the cascaded combination is given as G of S. So here you can, what you can do is you can put K is equal to 1. Okay, so G of S is equal to, it will become, and also T is also given as 1. So 1 plus Ts, that is 1s by 1, so 1 plus s into 1 minus e to the power minus s ts divided by s the whole square into 1 over s into s plus 1. So what happens here? There is an s plus 1, here there is a 1 plus s, or it is s plus 1 itself, as these two get cancelled, and you will have the result as g of s as 1 minus e to the power minus ts the whole square by s square into 1 by s into s, that s plus 1 has gone, 1 by s. So here this is 1 minus e to the power minus ts the whole square. I am taking out the bracket, so the denominator also have a square, so that is by s square, and this s also, so that it will be s cube. So gz is equal to z transform of g of s, that is equal to what? You can directly take that z is equal to e to the power st, so e to the power minus ts will be z to the power minus 1. So 1 minus z to the power minus 1 to the power 2, that is this one along, and z transform of 1 over s into s square, that is s cube. So what is the z transform of 1 over s cube? That is actually the parabolic input, that is r of k by 2. Okay, so the transform of 1 over s cube will be equal to t square by 2 into z plus 1 by z minus 1 the whole cube. Okay, so 1 minus z to the power minus 1 the whole square into 1 by 2. So as t is equal to 1 by 2 into z plus 1 by z minus 1 the whole cube. So here z minus 1, here if I multiply inside the bracket as z, it is z minus 1 by z. So z minus 1 by z the whole square will be z minus 1 the whole square by z square into 1 by 2 into z plus 1 by z minus 1 the whole cube. So this z minus 1 the whole cube and z minus 1 the whole square will get cancelled. You will end up with the denominator as z minus 1 and the numerator as z plus 1. Okay, also half is there, half you can take it out. And here also 1z and z square get cancelled, remaining in the denominator will be z. So z plus 1 by z into z minus 1. So this is your gz. This is not the pulse transfer function. Please note that gz is not equal to the pulse transfer function. So the pulse transfer function is equal to C of z by R of z is gz by 1 plus gz. This is the closed loop transfer function. Closed loop transfer function in the discrete domain, that is a transform domain. So that is the gz is the open loop transfer function. So you know that is cz by gz for a unity feedback system. That is, for this example it is unity feedback. Otherwise it will be, if it is having h of z also, then you will have, sorry, so here you will have g of z by 1 plus gz into hz. As hz is 1 here, it is g of z by 1 plus gz. So gz you have found as 1 by 2 into z plus 1 by z into z minus 1. What will be the pulse transfer function? It is not equal to gz. It is gz by 1 plus gz. So it will be like the gz you have already found, that I told you, half 1 by 2 into z plus 1 by z into z minus 1 divided by 1 plus half into z plus 1 by z into z minus 1. So that is 1 plus gz hz is 1. So multiply the numerator and denominator by z into z minus 1. You will have 1 by 2, okay, that is half into z plus 1 divided by, you have to multiply this 1 into z minus 1. So it is z into z minus 1 plus half into z plus 1. This half into z plus 1, this will go. So the 1 by 2 I am taking out, and z plus 1 by, you expand this, that is z square minus z plus this also you expand, half is z plus half. So minus z plus half is z. Minus z plus half is z will be minus half is z. Okay. So the denominator comes as z square minus half is z plus 1 by 2. So this you can, like, this is a university question which is asked for 15 marks. So very simple if you know, but if you don't know, you cannot write. That's the thing. So please go through the other questions, that is the examples. This example also you can find the similar way. It is instead of 1 by s into s plus 1, and also it is not giving you as the zero order hold is the first order hold or zero order hold. It is not given you. Usually if the question doesn't say it as first order or second zero order hold, by default you can take it as zero order hold, which is the simpler one. Okay, so please do it by your own and check. Okay, it is given t is equal to 0.1 second also. Okay, and the stability you will do it in the next class. So this also, these things also, please go through that. And so with this lecture is winding up. Okay, please go through the full recorded lecture, and also please try to do by your own. Take the question, try to do by your own. The other university questions also I have mentioned in this slides, that is coming in this module 3. Okay, that is the pulse transfer function, and also the steady state error for non-unity feedback system, that is Kp, Kv and Ka. If you want, you can put Kp dash, Kv, Ka dash and Kv dash. Don't confuse with the static error constants of unity feedback, because the static error constant and the steady state error is defined under unity feedback only. If you are given a non-unity feedback, then you have to make it a unity feedback by doing that analysis that we have done in this recorded lecture. Okay, thank you.